86,400 seconds per day. And so multiply times 28, and we get the number of seconds in the period of the moon's orbit around the Earth.
2,419,200.
All right.
Count the 2 million.
So that's equal to r cubed over 2419200 squared. All right. So what is this fraction on the left-hand side equal to? And by the way, if you don't have a calculator right now, please make sure you know how to use your calculator when dealing with exponents, when dealing with the times 10 to the negative 11th.
Times 10 to the 14.
All right, and that's going to be equal r cubed over that other number squared. So my r cubed, so r is going to be the cubed root of 9.84 times 10 to the 14th times 2419200 squared.
It's 1.8 times 10 to the 9.
1.8 times 10 to the 9th
Yeah.
units?
Meters.
I hope so. All right, and the actual distance from Earth to Moon. Units. Can you want to look that up quickly? I could also turn on this.
It is 238,900 miles.
200.
38,900 miles.
384 million meters.
384.4
million meters.
Oh, you were looking for it.
384.4.
Million meters, yeah.
Wow, that's farther off than I was expecting. Because that would be 3.84 times 10 to the 8th meters.
You divide by 4 pi squared.
Yes.
It's just that
Do we have confirmation of any of this stuff here? Anyone else get? That's the distance from Earth to the Moon.
I got a different number for that.
You got a different number here?
Yeah.
What is this?
I got 1.01 times 10 to the 13th.
Well, we'll take care of order of magnitude there. That should give us better results. So what do we get as our prediction then? Physics has a way of choking people up. I mean, this is just absolutely wonderful stuff.
It's actually fascinating. What did you ask again?
So we got a different, so this was the first thing that I was told right here, and then I was told that a different value, which actually I think is gonna get us closer to this.
I got 389 million, 0.5.
389 million, that's 389 times 10 to the 8 meters versus 3.84. All right, So much closer.
Got a cube root on the TI-82.
You can always raise it to the 1/3 power.
Yeah, you can also go into your math key and it should be number 4.
All right. Now, we're not exactly on probably the biggest issue. The two biggest issues are, one, it's not 28 days exactly, and two, it's actually not a circular path, it's an elliptical path. But hopefully good enough. Now, we do have two results. I'm obviously leaning towards the one that gets us closer to what I was expecting. But, yes, Cooper?
How did we get v squared over r for the acceleration?
How did we get that with the acceleration?
Yeah.
Because the moon is traveling in a circular path, the acceleration would be centripetal acceleration. And the formula for centripetal acceleration is v squared over r.
I think I was on here when that was.
Oh, okay.
And that's universal, so the centrifugal acceleration will always be v squared over r.
Or omega squared r. Okay. Centripetal acceleration is the speed of the object that's traveling in the circular path divided by the radius of the path, or the angular speed squared times r. And this comes from the relationship that v is equal to omega r. Which stems from the fact that S equals the relationship between the arc length and the angle. Questions to hear? Cooper?
Just why'd you feel like I can't wrap my head around it, but when we're in like the very first step, when we said f of g equal to the mass of the moon has the centripetal acceleration, why do we choose the mass of the moon over the mass of the earth?
Because when you're plugging into F equals ma, this is, I have some object that forces are acting on.
Yep.
So the forces are acting on that mass.
Okay.
And so, I guess the drawing is gone, but hopefully you can picture moon going around Earth. We were looking at the path of the moon.
So it's because we're finding the forces that are acting, or the force that's acting on the moon.
Right, therefore we use the mass of the moon. And it's because because the Earth is so much more massive than the moon is, we use the approximation that the moon's traveling in a circular path is much more appropriate approximation. Other questions?
Jesus kills me.
All right. That's pretty much it for 1B. It's a question of test. I mean, obviously, I'm still assuming that you're watching the video since most of the class is online. I think originally in the schedule, the test was scheduled for next week. If we push it off another week, then that puts us really close to the end of the semester. How does Wednesday the 19th sound, a week from today? We got one vote of enthusiasm, yes. I assume that was enthusiasm.
Yeah.
Okay.
Seems manageable.
All right. Test 1B,
Is next Wednesday?
next Wednesday.
Sweet.
She said sweet, sour, sour.
How many total tests will we have?
There'll be 4 test grades in the end. We're not done, just so you know. Don't give me that look.
You go home.
All right, so let's talk about something that might seem different, but isn't. So if I've got multiplying two binomials together, flash back to algebra 1, pre-algebra, whenever this is done. What is that equal to?
A squared minus B squared.
Yep. For those who don't see it immediately, if you FOIL, multiply the first one, a squared, outer, minus AB, inner, plus AB, final, or last, minus B squared. Those cancel out, left with A squared minus B squared. Usually I wait till we face this problem later, but I will just get it out of the way now. So what I'm gonna do is, I'm gonna start out with Newton's second law. F equals ma. Now I'm assuming that the object is actually going to move, that this net force, this is a total force here, so this is the total force, as is appropriate for Newton's second law, the total force acting on some mass. And I'm going to assume that since the total force, I'm assuming is not zero, this object is going to move through some displacement. So what I'm going to do is I'm going to multiply the force, I'm going to multiply both sides times the displacement. Now my multiplication here is, I deliberately have a dot in between them. It is called a dot product. It is also known as a scalar product. And inner product also, but we're not worried about that one. Called a dot product because the dot is the symbol. It's called a scalar product because when we multiply them, we'll get a scalar. And that should be equal to mass times the acceleration dot delta x. Math people still allow us to mostly multiply both sides by the same thing in the same way. We're good.
Why are we multiplying by the displacement again?
Because I know where we're heading. It would seem, right now, I do acknowledge that it seems arbitrary and why that, but I am actually heading towards someplace on this. Now, on the right-hand side here, I have the acceleration times the displacement. Well, let's think about the equation of what is acceleration. Let's just assume constant acceleration for the sake of this derivation. What is acceleration equal?
Delta E over delta T.
All right, so we have a change in velocity over the change in time, which is just V final minus V initial over, I'm just going to write time. And displacement. We have two equations for displacement.
Final position minus initial position over time.
No.
Okay.
If we wanted to go that route, it would just be final position minus initial position. No time. But from the cake formulas, the one that does not have time squared in it.
Isn't it VF minus V, or VF plus VI divided by 2 times acceleration?
Divided by 2 times what?
Acceleration.
Not acceleration.
Times time?
Times time. All right, so we've got these two formulas right here that I'm just going to plug into here. So this becomes hopefully dark enough to see, mildly better. So it's mass times Vf minus Vi divided by time, dot product, Vf plus Vi over 2 times time. Well, time cancels out, which is convenient. And that dividing by 2 is same as multiplying by half. It's just a scalar. I'm just going to factor that. I'm just going to bring that out. And so what I'm left with then is 1/2 times the mass times VF minus VI dot product VF plus VI. Hopefully you can see a connection of why I did the A plus B, A minus B earlier. Let's justify one of the, why this will be equal to 1/2 M. This will be VF squared minus VI squared. All right, so let me justify some of that. First off, there's two ways of multiplying vectors. One's called a dot product, the other one's called a cross product. If I have two vectors like this that I'm going to multiply, so let's call that vector A and vector B, and there's some angle in between them. Well, recognize part of A is in the direction of B and part of it is perpendicular to B. So I can break A up into parts. So I got part of A that's in the direction of B and part of it that's perpendicular to it. So this right here would just be the magnitude of A times the cosine of the angle. And this part right here would be A times the sine of the angle. When you're dealing with dot products, you're multiplying the parts that are in the same direction. So A dot B would be the magnitude of this part of A times the magnitude of B. So this would be A cosine of theta times B, or AB cosine theta. Recognize if I did B dot A, I would get the same thing. If I wanted to take it, this approach more literally, if I have A like this and B like that, and I break B up, part of B is in the direction of A and part of it is perpendicular to it. This line right here, that's B. This is a right angle there. This is B times the cosine of theta, B times the sine of theta. So if I multiply the parts that are in the same direction, I get B cosine theta times A, which is just AB cosine theta. So one of the key ingredients here, or one of the key properties, is that the dot product is, the commutative property holds for dot products. In other words, it doesn't matter the order in which I multiply. The scalar equivalent, 2 times 3 is equal to 3 times 2. Unless, of course, the usual, the math people lied to us. So when I FOIL this, I get VF times VF. And then outer plus VF dot VI minus VI dot VF minus VI dot VI. So these terms right here would cancel out because it doesn't matter the order in which I multiply them. VF times VI is the same as VI times VF. Now we're left with those two outer bits, VF times VF. If I take a vector, I don't care what, any vector, we'll call that A. And then I'm going to take the identical vector, A. So if I do a dot product with itself, well, it's the magnitude of one vector times the magnitude of the other vector times the cosine of the angle between them. Well, what's the angle between?
0.
And what is the cosine of 0?
1.
So what we're left with is just A squared. Lo and behold, that's what we have over here. get VF squared minus VI squared. And so what we have is this it's actually a really important equation, although it might not seem like much, that the force times the displacement is equal to 1/2 mass VF squared minus VI squared. Questions before I actually connect it with some vocabulary? Let's connect it to the vocab. We have this total force. Again, this is the total or net force times the displacement is equal to 1/2. I'm going to go ahead and distribute this 1/2 mv final squared minus 1/2 mv initial squared. Now 1/2 mv squared showed up twice. Physicists hate writing, or they want to write efficiently, and so they said, you know what? Let's just come up with another letter for that. Instead of having to write 1/2 mv squared, why don't we just use this letter, capital K, be equal 1/2 mv squared. So we got this over here, this force times displacement. Therefore is equal to this K final minus K initial. If I got minus my initial, that's just change. Now there's still too many letters for physicists, so they said, you know what, let's take this one step further. Force times displacement, I think that's going to show up quite a bit, so why don't we give that another letter? One of the reasons I don't use capital W for weight. This W here is for work. Matter of fact, this is the total work, because that's the total force. This is in this case, it actually went right down tot right there for total, or net work. So we have this idea of this net work is equal to this change in K. This is known as the work energy theorem. K is the formula, this 1/2 mv squared, this is kinetic